Welcome to the section 2.5 pre-class video assignment. In this section, we're going to learn about reduction of order as a method for solving certain differential equations. The method is, again, making a clever substitution and sticking it in and seeing what has to be true in order to determine a solution, but it works in a slightly different way. We will be seeing a little further on in this section, we do have a couple of by parts to look at. So I'm going to start you off today with a couple of by parts problems from my open math. So the first one should be, just for practice, the first one should be fairly easy. The second one is maybe a little bit more challenging, but give that a go. All right, so those were some integrals we're going to run into later in this section. But let's introduce the concept of reduction of order. So again, we are using reduction of order to solve DEs of the form like this guy, or if you've taken P0 and divided it through, it might look like this guy. Notice that we're actually not claiming that the forcing function f of x is equal to 0. It can be 0. So in theory, that forcing functions, if they are 0, the method can be applied to non-homogeneous and homogeneous equations. So the method ultimately depends on us being able to at least find a known complementary solution. The idea is simply this. Suppose you have a known solution to the homogeneous differential equation. The idea is to just assume that a solution to a non-homogeneous related equation has the form some function u of x times the known solution y1. So this is kind of where this method starts. We have an assumption that we have u of x, an unknown u of x times y1 of x, and our goal is to figure out what u of x must be to make this work. For brevity, and just for not so tedious to write the whole thing out, we will write that our substitution is y equals u y1. But remembering that both u and y1 are functions of x, or functions of the independent variable. So again, the usual approach then is, if this is our assumption as a solution, then we want to substitute it in and see if we can figure out what u is. In order to substitute this into our DE, clearly we need to find its first and second derivatives. So that is our first step here. I need to find y prime, but of course, y prime, if u and y1 are both functions of the independent variable, then derivative y prime is a product rule situation. So you have to differentiate by the product rule. And then once you have y prime, we will also need to find y double prime. Again, a couple of product rules this time, but that might simplify out a little bit. So that is our first step here in this method. We have to come up with a complementary solution y1. We form this as our guess. We need to find y prime and y double prime. So I'm going to have you try a couple of these. That is, I'm going to give you a couple of examples where you are going to find the derivatives of u times a particular y1 function. So give that a go. And then there's a second one to try as well. Okay, so again, just for practice, we will be seeing that kind of thing every time you do one of these examples. All right, so let's say we found, even in color here, let's say we have our y1 and we have, our y prime and our y double prime. What we do with them is we plug them in to the DE. So here is my y double prime plugged into my DE. Here's my y prime plugged in. Here is my y plugged into the DE. And again, as a solution, assuming this is a solution, this has to be equal to f of x, of course. So the clever bit then is to find is the following. We need to rearrange this a little bit. Effectively, I'm going to again, this takes a little bit of seeing, but once you've seen the trick, we'll notice that if I separate out this times this, and then P1 times this, and P2 times this. So again, notice I'm focusing on the Y1 double prime, the Y1 prime, and the Y terms. If I peel those off, and leave everything else behind, then this is what gets left behind. P0 times this stuff, and then we would have P0 times this guy here, and then P1 times this guy, P1 times this guy, and P2 times this remains the way it is. Notice that then you can gather together this term, and this term. We can gather those three terms together and come up with this. Basically, they all have a common u in them, so you can factor out the u. Then what's left behind is P0 Y1 double prime, P1 Y1 prime, P2Y. So the clever bit here is to recognize that since Y1 is a solution to the homogeneous equation, when you plug it into the DE on the left-hand side, we will get 0. So that means that this whole term is going to go away. Notice what that means for us is that the u is going to go away. So this is really where the term reduction of order comes from. We used to have a u term in here, but because of this little trick, this will always go away. The u term will always go away. This leaves us with a DE like this one. And again, notice there is no u term anymore. There's a u double prime and a u prime. So the clever bit is to make this substitution. If we let another letter, pick another letter, let's say v is u prime, then differentiating on both sides, v prime is u double prime. If you substitute those in for u, we now have a first order DE for v. Then hopefully, fingers crossed, this is a first order DE that we can solve to get a solution for v. V is u prime, so then I can find u by integrating v. So integrate v to find u. So once we have found u, we can go back to the beginning and say, well, now I know what the solution is I was after. The solution y is this function we just found u times y1, the particular solution to the homogeneous that we started with. This is the trick. And again, effectively, this here is the actual reduction of order step. In this step here, we turn a second order DE in terms of u into a first order DE in terms of v, hence the name reduction of order. So that is the idea. So we will work on some of those problems in class. The last remaining exercise is to work through a scaffolded problem involving this reduction of order trick. So this is not a full-blown reduction of order problem from the beginning. It starts basically with the DE of this form and makes you do the reduction of order step to the end. But again, it is scaffolded, so follow the instructions and give that a go here. All right, so otherwise we will complete this packet. There's some more things to be said, some examples to do, and we will complete those together in class. Thanks.